Hello guys, so welcome back to my YouTube channel. So in this video I'm going to prove Laplace transformation of t to the n power. Here n is greater than 0 and n's are integers, right? Otherwise I can write this as like this, right? So okay. This proof can basically can be proved two ways. One method is induction, right? Induction method. The other way is actually proved by gamma function, right? Okay. Let's go to the proof. Okay, method done, right? Method done. It is induction. Okay. What is induction? So basically induction is you are proving some condition for some n value, and then you are assuming it is true for some p value. If it is true for p, and using that we are proving it is also true for p1, p plus 1. So basically after proving that, you can say for any n value it is true that condition, right? Okay, so I'm going to use this method such as induction. Okay, so what I need to prove is Laplace transformation of t to the n is equals to the condition the equation is n to the factorial over s to the n plus 1. Okay, this is what I am going to prove. So okay, now I am going to say is it I am going to check whether it is true for n equals 1, right? So if it is not true for n equals 1, I am going to start from n equals 2. Okay, n equals 1, it is Laplace transformation of t, right? This is what I know from the previous videos. I know it is 1 over s, right? Now I am going to check is it in this format, right? Is this in that format? Okay. I can write 1 as 1 factorial, right? 1 factorial equals 1. So I can write Laplace transformation of t is s square, right? Okay, now I can write 1 as 1 plus 1, right? Here n equals 1, right? And let's say this as what? This is n and this is n, right? This is in format n factorial over s to the n plus 1, right? So I can say it is true for n equals 1. True for n equals 1. Okay, I proved that. Now I am going to consider it is true for n equals p, right? Let's assume that it is true for n equals p. Here p is a positive integer. Okay, now I am going to assume this is correct. T to p power equals 1 p factorial over s to the p plus 1. I am assuming this is true, right? Okay, now I am going to find whether this is true for n equals p plus 1 as well, right? Okay, t to p plus 1. Okay, now I have to find this one. Now I am going to the basics. 0 to infinity t to the p plus 1 e to the minus st dt. Okay, Now I'm going to use integral by parts t to the p plus 1 d over dt e to the minus st over minus s dt when I plug the limits t to the p plus 1 e to the minus st over minus s 0 to infinity 0 to infinity e to the minus st over minus s times now I have to differentiate this term. It is p plus 1 t to the p plus 1 minus 1, it is p, right, dt. Okay, now I have actually, okay, let's consider this part t to the p plus 1. When I divide this by e to the st, it is t to the p plus 1 over e to the st, right? Okay, when I plug infinity there, it is such situation as infinity over infinity. Okay, that is basically not defined, so I have to write that as a limit. Okay, t approaches infinity, t to the p plus 1 over e to the st. There is a term 1 over minus s, right? There is that term. Since it is a constant, I am going to take that away. Okay, minus here also it is a constant, so I can take that out. 0 to infinity e to the minus st. P plus 1 is also a constant, right? Okay, p plus 1 over s. Yeah, okay, yeah, that is like that dt. Okay, and there is also 0 term, right? I plug this value, but I have to subtract that one, right? Minus t to the p plus 1 e to the 0. Yeah, okay, that's t is 0, so 0 to the p plus 1, it is actually what? This is 0, right? Okay, now I only left with this limit. Minus 1 now is since this is in not defined format, I can use L'Hopital rule, right? Use L'Hopital rule. By applying L'Hopital rule many times, let's say p plus 1, that is actually differentiation both up and down terms, right? Okay, t to the p minus p, right, over s times e to the st. Again by differentiation, p plus 1 times p times t to the p minus 1 s square e to the st. After many terms, t approaches what? 1. Then when I differentiate it again, it becomes 0, right? So this term really becomes what? This is 0, right? Okay, 0 minus 0 plus p plus 1 over s. 0 to infinity, I am going to write t to the p first, right? T to the p times e to the minus st dt, right? Okay, since this is 0, I am going to neglect that part. P plus 1 of s times 0 to infinity. Okay, I will write that here. This is what? This is Laplace transformation of Tp, right? Laplace transformation of Tp. I assume that Laplace transformation of Tp is p factorial over s to the p plus 1. So I can write p plus 1 over s times p factorial over s to the p plus 1. When I simplify those terms, okay, after I simplify those terms, p plus 1 times p factorial is 1. That is basically p plus 1 factorial over s to the p plus 1 times s is s to the p plus 2. Let's rearrange the terms. P plus 1, let's consider p plus 1 is a single term, p plus 1 plus 1, right? Isn't this also in p factorial of s to the p plus 1 term? Not in that format, right? It's in this, basically in this format, right? Okay, so I can say if it is true for n equals p, it is basically true for in n equals p plus 1, right? So I can say, right, like so I can basically say this, if true for n equals p, that implies true for n equals p plus 1, right? I proved it's true for n equals 1. So if it is true for n equals 1, p plus 1 is n equals 2. It is also true for n equals 2. So if it is true for n equals 2, I can say it is true for n equals 3. If it is true for n equals 3, it is also true for n equals 4. So this series, this sequence is go on. So this is basically induction, right? So I can say for all n in z plus true, right? So I can say by induction this is true for all n, for all n z plus, right? So positive numbers, positive integers. Okay, that is the induction proof. Let's prove this let's prove this term. No, let's prove this what let's prove this property by gamma function, right? Okay, method 2. Okay, before going to method 2, I can write that I have proved that Laplace transform of t to the p is t to the n is n factorial over s to the n plus 1, right? Here n is a positive integer. Okay, let's prove this by gamma function, right? Okay, that is basically method 2. It is gamma function. Okay, by gamma function, right? Okay, what is gamma function, right? It is a integral like that, like this, right? Gamma x dt. This is the integral of 0 to infinity t to the x minus 1 e to the minus t dt, right? This is the gamma function. There is a property that gamma n plus 1 is equals to n factorial, right? So gamma n is equals to n minus 1 factorial. So these are the properties I need to prove this property, right? Okay, let's go on, right? Okay, what I need is Laplace transformation of t to the n. This is 0 to infinity t to the n e to the minus st dt. Okay, let's say z is equals to st, then dz is equals to s times dt, right? Here s is a constant. Okay, s is greater than 0 and it is a constant. Okay, when t goes to 0, z approaches to it is also approaching 0. When t is approaching to infinity, is it approaching to what? Since s is a positive integer, this approaches to infinity. Okay, those are the boundary conditions. Those are the limits. So let's go on. Now I'm going to plug these values. Laplace transformation of t to the n equals to 1. This is the integral 0 to infinity. Now there is no t, it is z over s to the n times e to the minus st, right? It is minus z. Okay, dz dt is dz over s, right? dz over s. Since s is constants, I can plug those out, right? So here there is s to the n, there is s, so over s to the n plus 1, 0 to infinity z n e to the minus z dz. Okay, 1 over s n plus 1, 0 to infinity z. I can write this as n plus 1 minus 1 e to the minus z dz. Okay, let's see what is the gamma function is. It is t to the x minus 1 e to the minus t, right? Here I have n plus 1. Let's say x is equals to n plus 1. Then what is this? This is the gamma function, right? This is the gamma function of what? Gamma function of x, right? This is gamma, when this is x, this is gamma function of x. So I have here n plus 1. So this is what? This is gamma function of what? This is gamma function of n plus 1, right? I hope you guys understood, right? Okay. In the above, yeah, here I said gamma function of n plus 1 is n factorial, so I'm not going to prove that here. Okay, now I'm going to use that term. So this is n factorial. So I have n factorial over s to the n plus 1. Easy, right? I think it is easy to prove rather than using mathematical induction, right? So we have basically proved this one, right, in 2 methods. So I hope you guys understood what I did here. So in the next video we will discuss some examples. Thank you for watching.